Look at your hand. Turn it over slowly. The skin, the bones, the blood moving beneath the surface. Every atom in that hand has existed for billions of years. The carbon was forged in the heart of a dying star. The hydrogen is older still, pressed into existence in the first 3 minutes after the universe began. You're holding right now a piece of the very beginning. But here is the strange part. Here is the part that keeps physicists awake at night, staring at equations that refuse to balance. According to everything we understand about the laws of nature, your hand should not exist. Neither should the rest of you. Neither should the earth beneath your feet, or the sun warming your face, or any of the 100 billion galaxies scattered across the observable universe. None of it should be here. The math is precise. The prediction is clear. When the universe ignited 13.8 billion years ago, it should have created exactly equal amounts of matter and antimatter, and those two substances, perfectly matched, should have found each other within the first second. They should have touched, and in that touching, they should have annihilated completely, converting every particle back into pure energy. No atoms, no stars, no planets, no life, just an eternal sea of cooling radiation, expanding forever into darkness. That is what the equations predict. That is what should have happened. And yet here you are, breathing, thinking, listening to these words. Something went wrong in the first heartbeat of creation. Something broke the perfect symmetry. Something violated the deepest laws we thought we understood. And after 70 years of searching, nobody knows what it was. Tonight we are going to follow the strangest mystery in all of physics. Not a mystery about what we have discovered, but a mystery about why we exist at all. If this slow journey helps you settle into your evening, consider tapping that like and subscribe button. It is always appreciated. Now let us begin. The year is 1928. A young English physicist named Paul Dirac is sitting in his office at Cambridge University, working through the mathematics of the electron. He's 25 years old, painfully shy, and possessed of a mind so precise that his colleagues sometimes joke that he thinks in equations rather than words. Dirac rarely laughs at these jokes. He rarely laughs at anything. What he does instead is calculate. The problem he is wrestling with is one of reconciliation. Two great theories have emerged in the early 20th century, each one revolutionary, each one incomplete. The first is Einstein's special relativity, which describes how objects behave when they move close to the speed of light. The second is quantum mechanics, which describes the bizarre behaviour of particles at the smallest scales. Both theories work. Both theories are verified by experiment, but they do not speak to each other. They are written in different languages. Dirac wants to find a single equation that combines them, an equation that describes how an electron behaves when it moves at relativistic speeds, while still obeying the strange rules of quantum probability. It is the kind of mathematical problem that most physicists would approach through approximation, through compromise, through accepting that some things simply cannot be unified. Dirac does not accept this. Dirac wants the perfect equation. And in the winter of 1928, alone in his Cambridge office, he finds it. The Dirac equation, as it will come to be known, is a thing of extraordinary beauty. 4 components, 16 symbols, a structure so elegant that other physicists will later describe it as the most beautiful equation in all of physics. It predicts the spin of the electron. It predicts its magnetic moment. It unifies quantum mechanics and special relativity in a single mathematical sentence. But there is a problem. The equation has solutions that Dirac did not expect. In fact, it has twice as many solutions as it should. For every electron with positive energy, the equation predicts a corresponding particle with negative energy. For every particle spinning one way, there is a mirror particle spinning the other way. The mathematics is symmetric in a way that physical reality does not seem to be. Dirac stares at these extra solutions. He cannot make them go away. Every time he tries to remove them, the equation breaks. They are not mistakes. They are not artifacts of sloppy mathematics. They are predictions. The equation is telling him that something else exists, something he has never seen, something no one has ever seen. At first, Dirac thinks these negative energy solutions might describe protons, the positively charged particles in the nucleus of atoms, but the math does not work. Protons are nearly 2,000 times heavier than electrons. These mirror particles should have exactly the same mass as the electron. The same mass, but with opposite charge. The same mass, but spinning in the opposite direction. The same mass, but fundamentally different in some way that the universe seems to distinguish. It takes Dirac 2 years to accept what his equation is telling him. In 1931, he publishes a paper making an extraordinary claim. There exists, he writes, a particle that no one has ever observed. It has the same mass as the electron but carries a positive charge instead of a negative one. If it ever meets an electron, the two particles will annihilate each other, converting their combined mass into pure energy. He calls it the anti-electron. The physics community is skeptical. Dirac is predicting the existence of something that has never been detected, something that no experiment has ever hinted at, something that emerges purely from the requirements of mathematical consistency. It is a bold claim. Some say it is an arrogant one. Mathematics alone, his critics argue, cannot tell us what exists. Only experiment can do that. And then, 1 year later, experiment does. Carl Anderson is working with cosmic rays at the California Institute of Technology. Cosmic rays are high-energy particles that rain down constantly from space, the debris of distant stellar explosions, accelerated to tremendous speeds by magnetic fields threading through the galaxy. When these particles slam into Earth's atmosphere, they produce showers of secondary particles. By placing detectors at high altitudes, physicists can study these cascades, catching glimpses of particles moving far faster than any laboratory accelerator can produce. Anderson has built a cloud chamber, a device filled with supersaturated vapour. When charged particles pass through the vapour, they leave trails of tiny droplets visible to the eye and recordable on film. A magnetic field curves the paths of the particles, and the direction and tightness of the curve reveals the charge and momentum of whatever passed through. On August 2nd, 1932, Anderson develops a photograph that makes his heart stop. The image shows a curved trail, exactly like the trail of an electron, the same curvature, suggesting the same mass. But the curve bends the wrong way. It curves in the direction that a positively charged particle would curve, a particle with the mass of an electron, but the charge of a proton, but far too light to be a proton. Anderson checks his apparatus. He checks the magnetic field. He checks the orientation of the photograph. There is no mistake. He has captured something impossible, something that should not exist according to everything physics knew before Dirac's equation. He calls it a positron, the positive electron, the anti-electron that Dirac predicted 2 years earlier from nothing but mathematical symmetry. Let that settle for a moment. A 25-year-old physicist sitting alone with pencil and paper, working through the requirements of mathematical consistency, predicted the existence of a particle that no one had ever seen. Not because he observed it, not because any experiment hinted at it, because the equations demanded it. And 2 years later, a camera in California captured that exact particle, streaking through a cloud chamber, leaving a signature that matched the prediction perfectly. This is not how science is supposed to work. Science is supposed to begin with observation, then build theories to explain what is observed. Dirac reversed the process. He found the theory first. The universe caught up. But the discovery of the positron opened a door that physics has never managed to close. If the electron has an antimatter partner, what about everything else? What about protons? What about neutrons? What about every particle in the zoo of fundamental physics? The answer, it turns out, is yes. Every particle has an antiparticle. The proton has the antiproton, discovered in 1955 at Berkeley's Bevatron accelerator. The neutron has the antineutron, discovered a year later. The neutrino has the antineutrino. The quark has the antiquark. For every piece of matter in the universe, there exists a mirror image, identical in mass but opposite in charge and quantum numbers. And when matter meets antimatter, they annihilate. They convert their combined mass into energy with perfect efficiency, following Einstein's famous equation. One electron and one positron, meeting and touching, produce 2 gamma rays flying off in opposite directions. One proton and one antiproton produce a spray of lighter particles that quickly decay, leaving nothing but radiation. This is not a theoretical prediction. This is observed fact. Every particle collider in the world produces antimatter routinely. The positron is so well understood that it is used in medical imaging. When you receive a PET scan, the P stands for positron. A radioactive tracer is injected into your body, a tracer that emits positrons as it decays. Those positrons travel a fraction of a millimetre before they meet electrons in your tissue and annihilate, producing pairs of gamma rays that detectors capture to build an image of your internal organs. Antimatter is not exotic. Antimatter is not rare in the absolute sense. Antimatter is produced constantly, in cosmic ray showers, in radioactive decays, in high-energy collisions. The universe knows how to make antimatter, the universe makes it all the time, and this is where the problem begins. Picture the universe in the moment of its birth, not the popular image of an explosion in space, because space itself did not yet exist. Picture instead the emergence of everything from nothing, a point of infinite density and temperature, a singularity where the known laws of physics break down. This is the Big Bang, and it happened 13.8 billion years ago. In the first fraction of a second, the universe was a soup of pure energy. The temperature was so high that particles and antiparticles were being created and destroyed constantly, winking into existence in pairs, finding each other and annihilating, leaving only radiation, which then spawned new pairs. The process was in perfect equilibrium. For every electron that appeared, a positron appeared beside it. For every quark, an antiquark. For every particle of matter, a mirror particle of antimatter. This is not speculation. This is what the laws of physics predict. The process of pair creation treats matter and antimatter symmetrically. Energy converts into particle-antiparticle pairs at exactly equal rates. There is no preference built into the equations. There is no thumb on the scale. And yet, as the universe expanded, it cooled. As it cooled, the energy available for pair creation dropped. Eventually, the temperature fell below the threshold needed to create protons and antiprotons, then below the threshold for lighter particles. The era of pair creation ended. Whatever particles existed at that moment would be the particles the universe was stuck with. If the Big Bang had created exactly equal amounts of matter and antimatter, those particles would have found each other. In the hot, dense plasma of the early universe, a particle could not travel far before meeting its antiparticle. They would have touched. They would have annihilated. Every proton would have met an antiproton. Every electron would have met a positron. Every bit of substance would have converted back into radiation. The universe would have been left with nothing but light. A cosmos of photons, expanding and cooling, with no atoms to form, no stars to ignite, no planets to coalesce, no life to emerge. Just eternal emptiness, stretching forever. That is what the equations predict. That is what should have happened. It did not happen. Somewhere, somehow, in the first fraction of a second of the universe's existence, a tiny imbalance appeared. For every billion antiparticles, there were 1,000,000,001 particles of matter. An excess so small, it is almost embarrassing to state. 1 part in a billion. A rounding error in the cosmic accounts, but that rounding error changed everything. When the annihilation was complete, when every particle of antimatter had found its counterpart and vanished in a flash of gamma rays, that one leftover particle in every billion remained. Those leftovers, that residue, that tiny remainder that should not have existed, became everything. Every atom in your body, every grain of sand on every beach, every drop of water in every ocean, every star in every galaxy. All of it, everything that exists, is the 1,000,000,000th remainder of a cosmic annihilation that should have been complete. Put that in perspective for a moment. Imagine a war where 2 armies clash, each with exactly 1,000,000,000 soldiers. At the end of the battle, every soldier on one side is dead, and one soldier on the other side remains standing. That one survivor is you. That one survivor is the entire visible universe. The other 2,000,000,000 soldiers, the matter and antimatter that should have perfectly cancelled, are gone. They are now the cosmic microwave background, the faint glow of radiation that fills all of space, the echo of that ancient annihilation. We are not the victors of some cosmic struggle. We are the statistical error. We are what was left over. And the question that keeps physicists awake at night is simple. Where did that error come from? The problem has a name. It is called baryogenesis, from the Greek word baryon, meaning heavy. Baryons are the heavy particles that make up atomic nuclei, protons and neutrons. Baryogenesis is the process by which the universe came to have more baryons than antibaryons, more matter than antimatter, something rather than nothing. In 1967, a Soviet physicist named Andrei Sakharov outlined the conditions that any explanation of baryogenesis must satisfy. Sakharov was a remarkable figure, a designer of hydrogen bombs who later became one of the most prominent dissidents in Soviet history, winning the Nobel Peace Prize for his advocacy of human rights. But before his turn to politics, he was one of the most gifted theoretical physicists of his generation, and in 1967 he sat down to ask a simple question. What would it take for the universe to create an imbalance between matter and antimatter? He identified three conditions, three requirements that any physical process must meet if it is to explain why we exist. These conditions have come to be known as the Sakharov criteria, and they have guided the search for baryogenesis ever since. The first condition is baryon number violation. In the standard model of particle physics, every particle carries a property called baryon number. Protons and neutrons have a baryon number of 1. Antiprotons and antineutrons have a baryon number of -1. In every interaction ever observed in a laboratory, the total baryon number is conserved. You cannot create a proton without creating an antiproton somewhere. You cannot destroy a neutron without destroying an antineutron alongside it. The books always balance. But if the books always balance, then the universe could never have accumulated an excess of baryons over antibaryons. The imbalance requires the books to be cheated. There must be some process, some interaction, some rare and fleeting violation of the conservation law that allows baryons to be created without their antiparticle partners. Sakharov's first condition demands that baryon number conservation is not absolute. It must be violated, at least sometimes, at least in the extreme conditions of the early universe. The second condition is violation of C and CP symmetry. These are the symmetries that connect particles to their antiparticles. C symmetry, or charge conjugation, is the transformation that swaps every particle for its antiparticle. CP symmetry combines charge conjugation with a mirror reflection of space, a parity transformation. If the laws of physics were perfectly symmetric under these transformations, then any process that created extra matter would be exactly balanced by a process that created extra antimatter. The imbalance would wash out. But if C and CP are violated, if the laws of physics treat matter and antimatter slightly differently, then a small bias can emerge. Reactions that favour matter over antimatter can win out over reactions that favour antimatter over matter. The universe can develop a preference. The third condition is departure from thermal equilibrium. This is perhaps the subtlest requirement. If the universe were in perfect thermal equilibrium, with every process occurring at exactly the same rate as its reverse process, then any imbalance would be erased as quickly as it formed. You cannot build up an excess if the system keeps returning to its balanced state. The early universe must have passed through moments where equilibrium broke down, where the forward direction of a reaction was more common than the backward direction, where the arrow of time had a thermodynamic meaning. These are the three keys: baryon number violation, C and CP violation, departure from equilibrium. Without all three, the universe remains symmetric. Without all three, matter and antimatter stay equal. Without all three, we do not exist. And here is the remarkable thing. When Sakharov proposed these conditions in 1967, all three seemed plausible. The standard model of particle physics, which was still being developed at that time, appeared to contain mechanisms that could satisfy each requirement. The early universe was certainly out of equilibrium as it expanded and cooled. CP violation had been discovered in the decay of certain exotic particles, and there were theoretical reasons to believe that baryon number might not be perfectly conserved at the extreme temperatures of the Big Bang. For decades, physicists worked on models of baryogenesis that operated within the standard model, tweaking parameters, calculating rates, trying to make the numbers work. The goal was to show that the tiny imbalance we observe, 1 part in a billion, could arise from known physics, that we did not need to invoke anything exotic or unknown, that the explanation for our existence was already contained within the equations we had written down. They failed. The problem is not that the standard model lacks the ingredients Sakharov identified. The standard model does violate CP symmetry. This was discovered in 1964 when James Cronin and Val Fitch observed that certain particles called kaons decay slightly differently, depending on whether they are matter or antimatter. The effect is small but measurable. The laws of physics do not treat matter and antimatter identically. The universe does have a preference, encoded in the fundamental interactions. The problem is that the preference is too weak. The amount of CP violation in the standard model, when you plug it into the calculations for the early universe, produces an imbalance of matter over antimatter that is about 10 billion times too small. Not a little too small, not almost enough, 10 billion times too small. The standard model predicts we should exist, but only barely, only at a level far below what we observe. Put another way, if the standard model were the whole story, then for every 100 billion galaxies in the observable universe, there should be one galaxy's worth of matter. We should be 1/100th of 100th of a millionth of what we are. But we are here. All 100 billion galaxies, all the stars and planets and moons and asteroids, all the matter that makes up everything we can see. The math does not add up. The equations do not balance. And the second problem is even worse. The standard model does allow for baryon number violation, but only through a quantum mechanical process that is so rare it essentially never happens. The process involves something called a sphaleron, a kind of quantum fluctuation that briefly allows the usual conservation laws to be broken. In principle, sphalerons could have converted antimatter into matter in the early universe. In practice, they only operate efficiently at temperatures above a certain threshold, and by the time the universe cooled enough for the matter, antimatter asymmetry to freeze in, the sphalerons had already stopped working. The window of opportunity closed before enough asymmetry could be generated. The standard model has the right ingredients. It has CP violation. It has baryon number violation. It has the departure from equilibrium built into cosmic expansion. But when you run the numbers, the ingredients do not combine in the right proportions. The recipe fails. The cake does not rise. This is not a minor embarrassment for physics. This is not a small gap in our understanding. This is a failure to explain the most basic fact about the universe, the fact that it contains something rather than nothing. Every atom you will ever touch, every breath you will ever take, every moment of your existence, represents a question that physics cannot answer. Why do you exist? The honest answer is that we do not know. Let me try to give you a feel for how strange this is. Imagine you walk into a casino. The casino has a very simple game. You flip a coin, and if it comes up heads, you win $1. If it comes up tails, you lose $1. Perfect symmetry, fair odds, no house edge. You sit down and start flipping. Heads, tails, heads, tails, tails, heads. The money flows back and forth. Sometimes you're up a few dollars, sometimes down. But over thousands of flips, the laws of probability guarantee that you will hover around zero. The wins and losses cancel. Now imagine that after 1 billion flips, you count your money. And instead of being roughly even, you discover that you have won $1 million. Not by cheating, not by using a weighted coin, but from a fair coin with fair odds. $1 million of pure profit from a game that should average to zero. You would be right to be suspicious. You would demand an explanation. Something must have happened. The coin must have a slight bias. The casino must have made an error. The laws of probability must have been violated somehow. That is the situation physics finds itself in with the matter, antimatter asymmetry. The coin of the early universe should have been fair. Matter and antimatter should have been created equally and annihilated equally. The cosmic accounts should have balanced to zero. Instead, we have a universe full of matter and essentially no antimatter, and no adequate explanation for where that surplus came from. Something happened, something broke the symmetry, something tipped the scales in favour of matter, in that first fraction of a second before the annihilation was complete. And we do not know what it was. There are theories, of course. Physics does not lack for theories. In the decades since Sakharov laid out his conditions, dozens of mechanisms have been proposed to explain baryogenesis. Some invoke new particles that have never been detected. Some invoke new interactions that operate only at energies far beyond what any accelerator can reach. Some invoke exotic processes in the first trillionth of a second after the Big Bang, conditions so extreme that they may never be reproducible in any laboratory. One family of theories is called electroweak baryogenesis. This approach tries to make the standard model work harder. It looks for ways to enhance the CP violation, to strengthen the phase transition that occurred when the universe cooled through the electroweak scale, to squeeze more asymmetry out of the ingredients we already have. These theories are elegant because they require minimal new physics. They are also increasingly constrained by experimental data. The Large Hadron Collider has been searching for the additional particles and interactions that electroweak baryogenesis requires, and so far it has found nothing. The parameter space is shrinking. The walls are closing in. Another family of theories is called leptogenesis. This approach takes a step back from baryons and focuses on leptons instead, particles like electrons and neutrinos. The idea is that the early universe first created an asymmetry in leptons, an excess of electrons over positrons or neutrinos over antineutrinos, and that this leptonic asymmetry was later converted into a baryonic asymmetry through the Sphaleron processes mentioned earlier. Leptogenesis requires heavy particles called right-handed neutrinos that have never been observed. It requires CP violation in the decay of these particles. It requires a carefully tuned set of initial conditions. But it can, in principle, produce the right amount of asymmetry. The numbers can work. Still another approach is called Affleck-Dine baryogenesis, named after the physicists who proposed it. This mechanism operates through scalar fields, smooth configurations of energy that pervaded the early universe. If these fields carried baryon number, and if they evolved in a particular way as the universe expanded, they could have deposited a baryon asymmetry into the plasma, a residue left behind as the field relaxed to its ground state. Affleck-Dine baryogenesis is popular among theorists who study supersymmetry, a proposed extension of the Standard Model that doubles the number of fundamental particles. But supersymmetry itself remains undetected despite decades of searching. The theories multiply, the proposals accumulate, and none of them has been confirmed. We are left with a strange situation. We know that something happened. We know the conditions it must have satisfied. We have a menu of mechanisms that could have done the job. But we cannot point to the one that actually did. We cannot say this is why we exist. It is a little like being a detective who arrives at a crime scene, finds clear evidence that a crime occurred, interviews a dozen suspects who all had motive and opportunity, and then discovers that the statute of limitations has expired and the case will never be solved. The mystery remains open. The question hangs in the air. Why is there something rather than nothing? The universe knows the answer. We are still searching. Rest with that for a moment. Let the scale of the problem settle over you. You're made of atoms. Those atoms are made of protons and neutrons and electrons. Every one of those particles exists because 13.8 billion years ago, in a span of time too short to measure, the universe broke its own rules. It created slightly more matter than antimatter. The difference was tiny, 1 part in a billion, a whisper, a rounding error. But that whisper echoed forward through all of cosmic history. It became stars, it became galaxies, it became planets and oceans and forests and cities. It became you, and we do not know why. The Standard Model of particle physics is the most successful scientific theory ever constructed. It predicts the outcomes of experiments to 12 decimal places. It describes the behavior of quarks and leptons and bosons with extraordinary precision. It is verified by every particle collision, every nuclear decay, every interaction between matter and light, and it cannot explain why you exist. This is not a failure at the edges. This is not a small gap in some obscure corner of the theory. This is a failure at the foundation. The most basic question you can ask about the universe, why is there stuff rather than no stuff, remains unanswered. Some physicists find this troubling. They see it as evidence that the Standard Model is incomplete, that new physics must be waiting to be discovered, that the next generation of experiments will reveal the missing piece. They work tirelessly, building detectors, designing accelerators, searching for the faint signatures of particles that do not fit the standard picture. Other physicists take a different view. They point out that we are here, that the question has an answer whether or not we ever find it, that the universe did what it did, and we are the beneficiaries. They see the matter-antimatter asymmetry not as a failure of physics, but as a reminder that physics is still young, still incomplete, still reaching toward questions that may take centuries to answer. Both perspectives carry truth. Both perspectives capture something about what it means to do science at the edge of knowledge. And tonight, lying in the dark, you can hold both. You can feel the weight of the question without needing to resolve it. You can let the mystery be a mystery. The universe made something from nothing. It did so in a way that violated the rules we thought we understood, and that something includes you. Whatever happened in that first fraction of a second, whatever process tipped the scales, Whatever violation wrote your existence into the fabric of reality, it worked. You are here. The evidence of that ancient asymmetry is the fact of your breathing, your thinking, your quiet awareness in this moment. The cosmos performed a magic trick when it was less than a second old, and you, here, now, are the evidence that the trick succeeded. Let us continue further into this story. There are more questions waiting in the dark, and they grow stranger as we approach them. The questions do grow stranger, and the first one we must face is this. How do we know any of this happened at all? Think about what we are claiming. We're saying that 13.8 billion years ago, in conditions so extreme that our everyday language buckles under the weight of describing them, something went wrong. Or perhaps something went exactly right. The universe created a slight excess of matter over antimatter, and that excess survived to become everything we see. But how can we possibly know this? How can we reach back across nearly 14 billion years, past the formation of galaxies and stars and planets, past the cooling of the cosmos, past the moments when the first atoms formed, all the way back to that primordial fraction of a second, and say with confidence what happened there? The answer lies in light. Not the light from stars, not the light from galaxies, but something far more ancient. Something that has been travelling toward us since the universe was only 380,000 years old. Something that carries within it the fingerprints of everything that came before. Picture the early universe, not the very earliest moments, not the first fraction of a second we have been discussing, but a few 100,000 years later. By cosmic standards, this is still inconceivably young. If the entire history of the universe were compressed into a single year, this moment would occur in the first few hours of January 1st. But by the standards of the first second, it is an eternity later. At this time, the universe was still a glowing fog. It was hot, so hot that atoms could not form. Every time an electron tried to settle into orbit around a proton, a passing photon would slam into it and knock it free again. The universe was a soup of charged particles and light, all mixed together, all interacting constantly. Light could not travel far. It would scatter off the free electrons almost immediately, like a flashlight beam in dense fog. The universe was opaque, and then something changed. As the cosmos expanded, it cooled. There came a moment, 380,000 years after the beginning, when the temperature dropped below a critical threshold. Suddenly, electrons could bind to protons without being immediately knocked free. Atoms formed. Hydrogen atoms, mostly, with some helium mixed in. And when the electrons bound themselves into atoms, they stopped scattering light. The fog cleared. Light that had been trapped, bouncing endlessly between particles, was suddenly free to travel. It streamed outward in all directions, carrying with it information about the conditions at that moment. That light is still travelling. It has been travelling for 13.8 billion years, stretched by the expansion of space, cooled from a brilliant glow to a faint whisper of microwave radiation. We call it the cosmic microwave background. And when you tune a radio between stations and hear that gentle hiss of static, a tiny fraction of that noise is this ancient light, reaching your ears across all of cosmic history. The cosmic microwave background is our window into the early universe. It tells us the temperature at that moment, about 3000 Kelvin, hot enough to glow orange-red like the surface of a cool star. It tells us the density of matter and energy. It tells us the geometry of space itself, and, crucially, it tells us something about the imbalance we have been discussing. Here is what the cosmic microwave background reveals. When the universe became transparent, it was already made almost entirely of matter. There was no significant antimatter left. The annihilation had already happened. Whatever process created the excess had already completed its work. The light we see is the afterglow not of the creation of the asymmetry, but of its consequences. But we can learn more. By studying the precise pattern of temperature variations in the cosmic microwave background, tiny fluctuations of about 1 part in 100,000, we can work backward. We can calculate how much matter there was at that time. We can compare it to how much light there was, and from that ratio we can deduce something remarkable. The photons in the cosmic microwave background outnumber the atoms in the universe by about 1 billion to 1. Let that sink in. For every atom in the cosmos there are roughly 1 billion photons of background radiation, and most of those photons are not from stars. They are the remnants of that ancient annihilation. This is the smoking gun. This is how we know. When matter and antimatter meet, they annihilate into light. The billion photons for every atom are the ghosts of particles that found their antiparticles and ceased to exist. They are the vast majority that cancelled out, and the atoms, the 1 in a billion that survived, are the slight excess that remained when the annihilation was complete. We can run the numbers. If the universe had started with exactly equal amounts of matter and antimatter, and if there had been no process to create an excess, then everything would have annihilated. The annihilation would have been complete. There would be no atoms left, only photons. The ratio would not be 1 billion to 1. It would be infinity to 0. The universe would be light and nothing else. Empty. Silent. Without form or structure or the possibility of complexity. But that is not what we observe. We observe atoms. We observe matter. We observe galaxies and stars and planets, and the chemical complexity that leads to life. The ratio is not infinite. It is precisely measurable, and from that measurement we can calculate the size of the original asymmetry. 1 extra particle of matter for every billion particle-antiparticle pairs, 1 in a billion. This is not a rough estimate. This is not an approximation. This is a number we can extract from the cosmic microwave background with considerable precision. We know how much matter exists. We know how much light exists. We know the relationship between them. And working backward, we know the size of the imbalance that set everything in motion. The universe has written its own history in light, and we have learned to read it. But knowing the size of the asymmetry is not the same as knowing its cause. We have measured the result. We have not explained the mechanism. It is as though we have found a bank vault that was robbed of exactly $1 billion, and we know the robbery happened, and we know precisely how much was taken, but we have no security footage, no witnesses, no fingerprints. We know the crime occurred. We cannot prove who committed it. Now, let us go deeper into the moment itself. The asymmetry was created in the first second of the universe, but the first second is not a single undifferentiated instant. It is a layered epoch, divided by physics into distinct eras, each governed by different forces and populated by different particles. To understand when the asymmetry might have formed, we need to understand the structure of that first second. In the very beginning, at times so short that our words for them become almost meaningless, the universe was unimaginably hot and dense. All 4 fundamental forces, gravity, electromagnetism, the strong force and the weak force, may have been unified into a single force. Particles as we know them did not exist. Space itself may have been different in ways we cannot picture. This is the realm of quantum gravity, where our 2 great theories, general relativity and quantum mechanics, collide, and neither can describe what happens. We have no complete theory of this era. We can only speculate. As the universe cooled, the forces separated. Gravity first, then the strong force, then finally the electromagnetic and weak forces, which remained unified longer than the others. At each transition, the character of the universe changed. New particles became possible. New interactions switched on or switched off. The physics itself was evolving moment by moment as the temperature dropped. By about 1/trillionth of a second after the beginning, the universe had cooled enough for quarks to exist as distinct particles. But they were not yet bound into protons and neutrons. They moved freely through a strange state of matter called quark-gluon plasma, a soup so hot and dense that the normal rules of confinement did not apply. This is the state we recreate, briefly and in tiny volumes, in particle colliders like the Large Hadron Collider. When gold nuclei or lead nuclei are smashed together at near-light speeds, they briefly produce droplets of quark-gluon plasma, echoes of that ancient epoch. These experiments tell us that the plasma was real, that it had specific properties, that the physics of that moment can be tested. Somewhere in this era, or perhaps earlier, the asymmetry was born. Let me put that in perspective. The entire epoch we're discussing, from the separation of forces to the confinement of quarks into protons and neutrons, lasts less than 1/millionth of a second. The conditions change faster than any process we can directly observe. The temperature drops by orders of magnitude. The dominant particles shift from one type to another, and somewhere in this blur of transformation, 1 extra quark in every billion quarks and antiquarks failed to find its partner. 1 extra quark that would later become part of a proton. 1 extra proton that would later become part of a hydrogen atom. one extra hydrogen atom that would later burn in a star and forge heavier elements, one extra grain of matter that would eventually contribute to the structure of everything you have ever seen or touched. The chain of causation is unbroken. From that first fraction of a second to this very moment, the matter has persisted. The asymmetry has propagated, and we are the inheritors of that ancient violation. But here is where the mystery deepens. Because when we look at the physics we understand, the physics of the Standard Model, we find that it almost works. It almost explains the asymmetry. The pieces are there, the mechanisms exist, the ingredients are present. But when we run the calculations, the numbers come out wrong. Not wrong by a small amount. Wrong by many orders of magnitude. This brings us to the three conditions that Andrei Sakharov identified in 1967. Sakharov was a Soviet physicist, brilliant and troubled, who would later become a dissident and a human rights advocate. But in 1967 he was thinking about the early universe. He was asking the same question we are asking. How could an imbalance between matter and antimatter arise from a universe that began in balance? Sakharov realized that three conditions must be met. First, there must be a process that violates something called baryon number conservation. Baryon number is a bookkeeping tool physicists use to count the difference between matter and antimatter. Protons and neutrons have a baryon number of +1. Antiprotons and antineutrons have a baryon number of -1. If baryon number is always conserved, then the total difference between matter and antimatter can never change. Whatever you start with, you are stuck with. So if the universe started with 0 net baryons, equal matter and antimatter, it would stay that way forever. For an imbalance to arise, baryon number conservation must be violated. Second, there must be processes that violate two symmetries called C and CP. C is charge conjugation, which swaps particles for antiparticles. CP combines charge conjugation with parity, which swaps left and right. If the laws of physics are perfectly symmetric under these transformations, then any process that creates excess matter will be exactly balanced by a mirror process that creates excess antimatter. The universe would stay in balance. For an imbalance to arise, these symmetries must be broken. The laws of physics must treat matter and antimatter differently. Third, these processes must occur out of thermal equilibrium. This is perhaps the subtlest condition. If the universe is in thermal equilibrium, every process is balanced by its reverse. Particles are created and destroyed at equal rates. Any asymmetry that forms in one reaction is immediately erased by the reverse reaction. Only if the universe is changing faster than these reactions can keep up, only if conditions are moving out of equilibrium, can an asymmetry persist. These are the Sakharov conditions. And here is the remarkable thing. The Standard Model satisfies all three of them. Baryon number violation. It exists in the Standard Model. There are exotic processes, called Sphaleron transitions, that can change baryon number. They involve the weak force and occur at very high temperatures. In the early universe, they would have been active. CP violation. It exists in the Standard Model. We have measured it in the decays of certain particles called kaons and B-mesons. The laws of physics do treat matter and antimatter slightly differently. The symmetry is broken. Out of equilibrium conditions, they existed in the early universe. As the cosmos expanded and cooled, various transitions occurred that took the universe out of equilibrium. The conditions were met, so the Standard Model has all the ingredients, the recipe is there. But when we try to cook with it, we produce almost nothing. The amount of CP violation in the Standard Model is too small. The baryon number violation happens too slowly. The out-of-equilibrium conditions are not dramatic enough. When we calculate how much matter-antimatter asymmetry the Standard Model can produce, we get a number that is 10 or 11 orders of magnitude smaller than what we observe. Let that settle. The Standard Model predicts an asymmetry. That is already remarkable. It does not predict 0, but it predicts a number so small that the universe should contain essentially nothing. The atoms in your body, the stars in the sky, the galaxies scattered across billions of light years, none of this should exist if the Standard Model is the whole story. Something else must have happened. Some physics beyond the Standard Model must have operated in that first fraction of a second, amplifying the asymmetry, tipping the scales more dramatically than our best theory can explain. This is why physicists build ever more powerful colliders. This is why they study ever more exotic particles. This is why they search for hints of new physics in the precise measurements of known particles. Somewhere, hidden in the data, There may be evidence of the process that created us, the violation that wrote our existence into reality, the broken symmetry that made something from nothing. We do not know what that process was. We have theories. We have candidates. Physicists have proposed dozens of mechanisms that could generate the asymmetry. Some involve new particles, some involve new forces, some involve modifications to gravity or extra dimensions or symmetries that are broken in ways we have not yet observed. Each theory makes predictions. Each theory can, in principle, be tested. But none of them has been confirmed. The search continues. Every year, new data from particle physics experiments, from cosmological observations, from precision measurements of atomic properties, constrains the possibilities. The list of viable theories grows shorter. The remaining candidates become more exotic, more difficult to test, more distant from our everyday experience of the world, and still we do not know. Here is something to rest with. The fact that you exist is a clue. The atoms in your body are evidence. Every particle of matter on Earth, every grain of dust between the stars, every galaxy in the observable universe is a data point in this cosmic mystery. The asymmetry is not hidden. It is everywhere. We are swimming in the evidence. We just do not know how to read it yet. But we are trying. That is what science does. It takes mysteries and works at them, generation after generation, until understanding emerges. The matter-antimatter asymmetry is one of the deepest mysteries in physics. It has resisted explanation for half a century, but the search has not stopped. The questions have not been abandoned. Somewhere, perhaps in a detector that has not yet been built, perhaps in a theory that has not yet been imagined, the answer waits. The universe knows what happened. It was there. It did what it did. And it left the evidence scattered across the cosmos in the form of every atom that exists. We are still gathering that evidence. We are still piecing together the story. And the story is not finished. Now let us turn to something even stranger, because the asymmetry is not the only puzzle hidden in that first second. There are other mysteries, other violations, other questions that grow more difficult the closer we look. The early universe was not just hot and dense, it was a factory of contradictions, and one of those contradictions involves the very particles we have been discussing. The particles we have been discussing, matter and antimatter, quarks and antiquarks, electrons and positrons. We have treated them as opposites, as mirror images, as two versions of the same underlying thing. And in most ways they are. An electron and a positron have the same mass, the same spin, the same magnitude of electric charge. They interact with gravity in exactly the same way. They respond to the electromagnetic force with equal strength. If you could build an atom entirely from antimatter, a positron orbiting an antiproton, it would behave almost identically to a normal hydrogen atom. It would emit the same wavelengths of light. It would form the same chemical bonds. It would obey the same quantum rules. Almost identically. That word carries a universe of meaning. Because there is a difference. A subtle difference. A difference so small that it took decades to confirm, and so profound that it may hold the key to our existence. Let me take you to a laboratory in Switzerland. Not the Large Hadron Collider, not the famous ring that spans the border between two countries, but a smaller facility, quieter, more patient. This is the antiproton decelerator. It is, in a sense, an antimatter factory. Physicists here create antihydrogen atoms, trap them in magnetic fields and study them with extraordinary precision. They are looking for differences, any difference. The slightest deviation from perfect symmetry. Picture the setup. A beam of antiprotons, slowed to a crawl, captured in a magnetic trap. Positrons, harvested from radioactive decay, cooled and compressed. The two brought together gently to form antihydrogen. Not much of it. A few atoms at a time, held in place by carefully shaped magnetic fields that exploit the tiny magnetic moment of the atom itself. The antimatter floats in a near-perfect vacuum, isolated from the ordinary matter of the laboratory walls, which would annihilate it instantly on contact. And then the measurements begin. Physicists shine lasers on these antihydrogen atoms. They measure the frequencies at which the atoms absorb and emit light. They compare these frequencies to the corresponding frequencies in ordinary hydrogen, which we have measured to 12 decimal places of precision. They are looking for a mismatch, a crack in the symmetry, any evidence that antimatter behaves differently than matter in ways that go beyond the charge reversal. The results so far are astonishing in their ordinariness. The antihydrogen atoms behave exactly like hydrogen atoms. The transition frequencies match to the limits of measurement. The symmetry holds. And yet we know the symmetry must be broken somewhere, because we exist. Because the universe is full of matter and nearly empty of antimatter, because something treated them differently in that first fraction of a second. This is the paradox that haunts modern physics. The symmetry is perfect in every experiment we can perform, and the symmetry must be imperfect in ways we cannot yet measure. Both statements are true, both are supported by evidence, and they point to physics we have not yet discovered. Let me introduce you to a symmetry, one of the deepest and most beautiful in all of physics. It is called CPT symmetry, and it is not optional. It is built into the mathematical structure of quantum field theory itself. Every known theory that respects the basic principles of relativity and quantum mechanics must also respect CPT symmetry. It is not a choice. It is a theorem. Here is what it means. Take any physical process, any interaction between particles, any decay, any collision, any transformation. Now perform 3 operations simultaneously. First, replace every particle with its antiparticle. Swap electrons for positrons, quarks for antiquarks, neutrinos for antineutrinos. This is called charge conjugation, and we label it C. Second, reflect everything through a mirror. Swap left and right, reverse all spatial coordinates. This is called parity, and we label it P. Third, reverse the direction of time. Run the process backward. This is called time reversal, and we label it T. CPT symmetry says that if you perform all 3 operations together, the resulting process must be physically identical to the original. The laws of physics must be the same. This is not an approximation. It is not a tendency. It is an exact mathematical consequence of the deepest principles we know. No experiment has ever found a violation of CPT symmetry. If one did, it would force us to abandon either special relativity or quantum field theory, or both. The foundations of modern physics would need to be rebuilt from the ground up. But here is the twist. While CPT must be conserved, the individual pieces do not have to be. C can be violated. P can be violated. Even CP, the combination of charge conjugation and parity, can be violated. And in fact, CP is violated. We have measured it. We have seen it with our own instruments. This is worth pausing over. The universe distinguishes between matter and antimatter, not in every interaction, not in most interactions, but in some processes the rules treat them differently. A particle decays one way, its antiparticle decays a slightly different way. The rates differ, the angles differ, the probabilities differ. The symmetry that seems so perfect in the laboratory reveals a hidden crack when you probe it deeply enough. This is one of Sakharov's conditions. Charge conjugation must be violated, CP must be violated. Otherwise, any process that creates excess matter would be perfectly balanced by an equivalent process creating excess antimatter, and the net asymmetry would remain 0. The Standard Model contains CP violation. We discovered it in 1964 in an experiment involving particles called kaons, and we have confirmed it many times since in more complex systems. The physics is real. The mathematics describes it precisely. The predictions match the observations, and it is not enough. The amount of CP violation in the Standard Model is too small, by many orders of magnitude. If we calculate how much matter-antimatter asymmetry this tiny CP violation can produce, we get a number that is far, far below what we observe. The crack in the symmetry exists. But it is not wide enough to explain us, so there must be more CP violation, more sources of asymmetry, more physics beyond what we have measured. Now let us follow a different thread, a thread that leads not to particle colliders, but to the most exotic laboratories in the cosmos. Because some of the best clues about matter-antimatter asymmetry may be hiding not in the debris of artificial collisions, but in the natural violence of the early universe itself. Consider the neutrino. For decades, physicists believed neutrinos were massless. The Standard Model treated them as weightless ghosts, particles that barely interact with anything, streaming through the universe in unimaginable numbers without leaving a trace. Billions of neutrinos pass through your body every second, emitted by the nuclear reactions in the sun, and virtually none of them touch a single atom on the way through. They are the universe's most antisocial particles, but they have mass. We know this now. The evidence came from a phenomenon called neutrino oscillation. the discovery that neutrinos change flavour as they travel. An electron neutrino produced in the Sun can arrive at Earth as a muon neutrino or a tau neutrino. This transformation is only possible if neutrinos have mass, small masses, almost unimaginably small, but real. And massive particles can have antiparticles. Here is where it gets strange. We do not know if neutrinos and antineutrinos are truly different particles, or if they are somehow the same thing. This is not a minor technical distinction. It is one of the deepest open questions in particle physics. Let me explain. For most particles, the distinction between matter and antimatter is clear. An electron has negative charge. A positron has positive charge. You can tell them apart by measuring their behaviour in an electromagnetic field. But neutrinos carry no electric charge. They interact only through the weak nuclear force and gravity. The usual signpost that distinguishes matter from antimatter is missing. There are two possibilities. Either neutrinos and antineutrinos are genuinely different particles, distinguished by some internal quantum property we call lepton number, or they are the same particle, and what we call an antineutrino is just a neutrino in a different state of motion. The second possibility has a name. We call such particles Majorana fermions, after the Italian physicist Ettore Majorana, who proposed the idea in 1937 and then vanished mysteriously a year later, never to be seen again. His idea outlived him. If neutrinos are Majorana particles, something remarkable becomes possible, a process called leptogenesis. Picture the very early universe, in the first fraction of a second after the Big Bang. Temperatures are beyond imagination. Energies are high enough that particles we have never directly observed can be created from pure radiation. Among these particles might be extremely heavy cousins of the ordinary neutrinos, particles with masses millions of times greater than a proton, particles that could only exist in the cosmic furnace of that first instant. These heavy neutrinos, if they exist, would be unstable. They would decay into lighter particles. And here is the key. If they are Majorana particles, and if CP is violated in their decays, they could decay into matter and antimatter at slightly different rates. More leptons than antileptons, more electrons than positrons. A tiny imbalance born in the death of these primordial heavy neutrinos. This lepton asymmetry would not stay separate from the baryon asymmetry, the imbalance between quarks and antiquarks. In the extreme conditions of the early universe, processes called sphalerons, which we discussed earlier, can convert lepton number into baryon number and vice versa. The two asymmetries are linked. An excess of leptons becomes an excess of baryons, and there you have it, a mechanism, a pathway from the chaos of the Big Bang to the matter that exists today. Heavy neutrinos decay asymmetrically, leptons outnumber antileptons, sphalerons redistribute the imbalance, baryons outnumber antibaryons. The universe cools, the sphalerons freeze out, and the asymmetry is locked in. One baryon survives for every billion annihilations, and those survivors become atoms, become dust, become stars, become planets, become you. This is leptogenesis. It is one of the leading theories for the origin of matter. It is elegant. It is testable, in principle. And it requires physics we have not yet confirmed. We do not know if heavy right-handed neutrinos exist. We do not know if ordinary neutrinos are Majorana particles. We do not know if CP is violated in the neutrino sector in the right way and by the right amount. Each of these is an open question. Each is the target of ongoing experiments. How do you test whether a neutrino is its own antiparticle? There is a way. A process called neutrinoless double beta decay. Imagine a nucleus that undergoes two simultaneous beta decays. Normally, each beta decay produces an electron and an antineutrino. Two decays, two electrons, two antineutrinos. But if the neutrino is a Majorana particle, something else can happen. The antineutrino from one decay can transform into a neutrino and be absorbed by the other decay. The two neutrinos annihilate each other internally. What emerges is just two electrons, no neutrinos at all. This has never been observed, but physicists are looking. Experiments around the world, deep underground to shield them from cosmic rays, are watching samples of specific isotopes, waiting for the telltale signal. Two electrons with a combined energy equal to the mass difference of the parent and daughter nuclei. No neutrinos to carry away the missing energy, a clean signature. The search has been going on for years. The limits have grown tighter. If neutrinoless double beta decay happens at all, it happens rarely. The half-lives involved must be extraordinarily long, more than 10 trillion years for the isotopes being studied. But the experiments continue, the sensitivity improves, and the question remains open. If we ever observe this decay, we will know that neutrinos are Majorana particles, we will know that lepton number is not perfectly conserved, and we will have opened a window onto the physics of leptogenesis, the physics that may have created us. Let that sit for a moment. The question of why matter exists may come down to the subtle quantum identity of the lightest particles we know. Neutrinos, those ghostly messengers that barely interact with anything, may hold the key to the existence of everything. There is a lesson here about the interconnectedness of physics. The questions that seem most abstract, most removed from daily life, turn out to be linked to the most fundamental facts about our existence. Why does anything exist? Why is there something rather than nothing? These are not just philosophical puzzles, they are scientific questions, and the answers may involve particles so elusive that detecting them requires detectors buried miles underground, shielded from the noise of the world, waiting in darkness for years on end. Let me take you to one of these detectors. Deep beneath the mountains of central Italy, in a laboratory carved out of solid rock, there is a hall called the Gran Sasso National Laboratory. It is one of the largest underground research facilities in the world. The mountain above provides a natural shield, blocking nearly all the cosmic rays that would otherwise drown out the delicate signals the physicists are hunting. In this hall there are experiments searching for dark matter, experiments measuring neutrino properties, experiments testing the most fundamental principles of quantum mechanics, and there are experiments searching for neutrinoless double beta decay. One of them uses a technique that is almost beautiful in its simplicity. Cylinders of enriched germanium, cooled to a fraction of a degree above absolute zero, suspended in a bath of liquid argon that is itself cooled and purified to an extraordinary degree. The germanium contains a specific isotope, germanium-76, which can undergo the decay the physicists are hunting. When a decay happens, the energy of the emitted electrons is absorbed by the germanium crystal, producing a tiny electrical signal that can be measured. The experimenters wait. They watch. They filter out every possible source of noise, every stray radioactive decay from the surrounding rock, every cosmic ray that slips through the mountain, every tremor from the Earth itself. They accumulate data over years, and they look for a peak, a specific energy, corresponding to the full energy release of the neutrinoless decay, appearing above the background. So far, nothing. The peak has not appeared. But the search is not over. The experiments grow more sensitive. The isotope samples grow larger, the background rejection improves, and the question remains alive. If the signal ever appears, it will be front-page news in physics. It will confirm a theoretical prediction that has waited nearly a century for verification, and it will tell us something profound about the first fraction of a second after the Big Bang, about the asymmetry that created us, about why the universe chose existence over annihilation. Now step back for a moment. We have travelled from the first microsecond after the Big Bang to laboratories deep underground in the present day. We have discussed heavy particles that may never have been detected, symmetries that must be broken but resist our measurements, and the most elusive particles in nature. The story is complex. The threads are many, but they all point in the same direction. The existence of matter is a clue. Every atom is evidence of something that happened at the beginning of time. We do not know exactly what happened. We have theories, we have candidate mechanisms, we have mathematical frameworks that could explain the asymmetry. But we have not yet found the smoking gun. We have not yet measured the new physics that created us. And so the search continues. In particle accelerators, in underground detectors, in telescopes scanning the sky for the faint afterglow of the Big Bang, in precision measurements of atomic transitions, in calculations that push the boundaries of mathematical physics. Every approach contributes a piece of the puzzle. Every null result narrows the possibilities. Every unexpected signal might be the breakthrough. This is how science works at the frontier. Not with sudden revelations, but with patient accumulation. Not with certainty, but with increasingly constrained uncertainty. The matter-antimatter asymmetry has resisted explanation for half a century. That is not a failure. That is the normal pace of deep science. Some questions take generations to answer. Some require instruments that have not yet been invented. Some require ideas that have not yet been thought. But the question is not unanswerable. It has an answer. The universe knows. The universe did what it did in that first fraction of a second, and the evidence is scattered across the cosmos in the form of every atom that exists. We are made of the answer. We just have not learned to read ourselves yet. And there is something quietly thrilling in that thought, something alive in the not knowing. The universe holds its secrets loosely. It leaves clues everywhere. It invites us to look. Now let us turn to another approach entirely, because while some physicists search for new particles and new forces, others are searching for something even more subtle. They are searching for tiny variations, almost imperceptible differences, in the behaviour of particles we already know. They are measuring things we thought we understood completely, and they are finding that the measurements do not quite match the predictions. This is the story of the muon, a particle that should not be interesting, a particle that should obey the standard model perfectly, a particle that is, instead, behaving strangely. The muon is the electron's heavier cousin. That is the simplest way to describe it. Take everything you know about the electron, for its charge, its spin, its fundamental identity as a lepton, and make it 207 times heavier. That is the muon. It appears in cosmic ray showers, in particle collisions, in certain radioactive decays. It lives for about 2/millionths of a second before it falls apart into an electron and two neutrinos. In the grand catalogue of particles, the muon occupies a peculiar position. It is not exotic. It is not rare. Physicists have been creating and studying muons for decades. Every major accelerator facility has produced billions of them, and yet the muon has become, in recent years, one of the most carefully watched particles in all of physics, because the muon is misbehaving, and no one can fully explain why. Let me tell you what the muon is doing wrong. Every charged particle that has spin also has a magnetic moment. You can think of it as a tiny bar magnet embedded in the particle, pointing in some direction, interacting with external magnetic fields. For the electron, this magnetic moment has been measured with extraordinary precision. It is one of the most accurately known quantities in all of science. And the standard model predicts the electron's magnetic moment to 12 decimal places. The measurement agrees with the prediction to 12 decimal places. This is often cited as the greatest triumph of quantum electrodynamics. Theory and experiment, aligned to a part in a trillion. Now consider the muon. The muon also has a magnetic moment. The standard model also predicts it. And for decades the prediction and the measurement were close enough that no one worried. But as the measurements improved, a discrepancy appeared. A small discrepancy. A persistent discrepancy. The muon's magnetic moment is slightly larger than the standard model predicts. Not by much. The difference is at the level of 2.5 parts per million. Imagine measuring something to incredible precision. Imagine a surveyor measuring the distance from New York to Los Angeles and finding that the result is about 400 feet longer than the blueprints say. That is the scale of the muon anomaly. Tiny, but real and unexplained. This measurement has a name. It is called the anomalous magnetic moment of the muon, or G-2 for short. The G stands for a quantity called the G factor, which describes how the particle's spin couples to its magnetic moment. For a simple point particle obeying basic quantum mechanics, G would equal exactly 2. But particles are not simple. They are surrounded by a constant haze of virtual particles, popping in and out of existence according to the rules of quantum field theory. These virtual particles affect the magnetic moment. They make tiny corrections to the value of G. The corrections are calculable from the standard model, and the sum of all those corrections, when compared to the measured value, should give 0. The standard model should predict exactly what we measure. For the electron it does. For the muon it does not. The discrepancy has been measured at multiple facilities over multiple decades. The most famous measurement came from the Brookhaven National Laboratory in the early 2000s. That experiment found a persistent excess in the muon's magnetic moment. The result had a statistical significance of about 3.5 sigma, not quite enough to claim a discovery by the strict standards of particle physics, but enough to raise eyebrows, enough to justify building an even more precise experiment. That experiment now exists. It is located at Fermilab outside Chicago. It uses a huge superconducting storage ring, originally built at Brookhaven and transported in one piece to Illinois, to trap muons in a circular path and measure their magnetic precession with exquisite accuracy. The muons travel around the ring at nearly the speed of light, their spins wobbling like tiny gyroscopes in the magnetic field. The rate of that wobble reveals the anomalous magnetic moment, and the Fermilab experiment has confirmed the Brookhaven result. The discrepancy persists. The significance has grown. The muon's magnetic moment does not match the standard model prediction at a level that is now approaching 5 sigma, the threshold physicists use to claim a discovery. Let that settle for a moment. The standard model, our best theory of particle physics, predicts a certain value for a measurable quantity. The measurement disagrees. This is not a matter of interpretation or philosophy. It is a number that should be one thing and is instead another. Something is affecting the muon that the standard model does not account for. What could that something be? This is where the muon anomaly connects back to our larger story. Because the virtual particles that affect the muon's magnetic moment include all the particles that exist, not just the ones we have discovered, but any particle that might exist no matter how heavy or how fleeting. When the muon sits in that magnetic field, its quantum haze extends outward into every possible state that nature permits. If there are new particles, new forces, new physics beyond the standard model, they will contribute to that haze. They will shift the magnetic moment. They will appear as an excess or a deficit in the final measurement. The muon anomaly, in other words, is a portal. It is a way to see beyond what we have directly detected. It tells us that something is out there, something we have not found in our colliders, something we have not seen in our detectors, contributing to the physics of this ordinary particle. The muon is feeling the presence of the unknown, and it is reporting back. Now here is where things become delicate. The prediction of the muon's anomalous magnetic moment is extraordinarily difficult to calculate. The standard model contribution involves adding up the effects of photons, electrons, quarks, gluons, W and Z bosons, and the strong force interactions of hadrons, particles made of quarks bound together. Most of these contributions are well understood, but one piece of the calculation has remained stubbornly uncertain. It involves the behaviour of hadrons in quantum loops, specifically the contribution from virtual hadronic vacuum polarization. This piece cannot be calculated from first principles with the same precision as the rest. It must be inferred from experimental data, or computed using a method called lattice, QCD, a numerical technique that simulates the strong force on a discrete grid of space-time points. And here is the complication. Different methods of estimating the hadronic contribution give different answers. The traditional approach, using experimental data from electron-positron collisions, gives one value. Recent lattice QCD calculations give a slightly different value. If the lattice calculations are correct, the discrepancy between the standard model and the measured muon moment shrinks. It might even disappear. So which is right? The experimental inference or the numerical simulation? This is an active debate in the physics community. Papers are published, conferences are held, results are scrutinized and reanalyzed. The answer is not yet settled. But regardless of the outcome, the muon anomaly has performed an important service. It has focused attention on the limits of our understanding. It has forced us to sharpen our calculations, to improve our methods, to demand greater precision from both theory and experiment. And it has reminded us that even particles we think we understand completely might harbour surprises. If the anomaly turns out to be real, if the final verdict is that the muon's magnetic moment truly exceeds the standard model prediction, then something new is required to explain it. That something might be a new particle, it might be a new force, it might be a subtle modification to the laws of physics at energies we have not yet probed. And whatever it is, it might also be connected to the matter-antimatter asymmetry. Because any new physics that couples to muons also couples to the broader structure of the standard model. Any new particle that affects the muon's magnetism might also participate in the processes that generated the asymmetry in the first place. This is the hope. This is why the muon anomaly matters beyond its immediate puzzle. It is a thread that, if pulled, might unravel a much larger mystery. Let me give you another thread. Another particle behaving strangely. Another measurement that does not quite fit. This time it is not the muon itself, but the muon's interactions with other particles. Specifically, physicists have been measuring how certain particles called bemesons decay. Bemesons are bound states of a bottom quark and another lighter quark. They are produced in particle collisions and live for about 1.5 trillionths of a second before they decay. That brief lifetime might seem impossibly short, but to modern detectors it is an eternity. The decays can be tracked, the products identified, the branching ratios measured with precision. According to the Standard Model, B mesons should decay to electrons and muons at essentially the same rate, once you account for the small differences in mass. This is a prediction called lepton universality. The electron, the muon, and the tau, the three charged leptons, should be treated identically by the weak force, differing only in their masses. The Standard Model does not care which lepton appears in a decay product. The coupling is the same, the rates should be the same, but the measurements, particularly those from the LHCb experiment at CERN, have sometimes shown discrepancies. Certain decay channels appear to produce fewer muons than expected, relative to electrons. The effect is subtle, a few % deviation from the predicted ratio. The statistical significance has fluctuated as more data has been collected. Some early hints have weakened, others have persisted. The situation remains unresolved. If lepton universality is violated, if the universe truly treats muons differently from electrons in certain weak interactions, then something profound is at work. The Standard Model would be wrong in a specific and measurable way. A new force or a new particle would be required to explain the preference. And once again, that new physics might connect to the matter-antimatter puzzle. Any force that distinguishes between leptons might also distinguish between matter and antimatter in ways the Standard Model does not predict. The pattern is becoming clear. The Standard Model is under pressure, not from a single dramatic failure, but from an accumulation of small tensions. The muon's magnetic moment, the B meson decay ratios, the neutrino oscillations that imply masses the original Standard Model did not include, the absence of the cosmic antimatter that the Standard Model predicts should exist. Each anomaly is small in isolation, each might have an innocent explanation, but together they form a constellation of hints. Something is missing from our picture of nature. Something is out there, just beyond the edge of what we can currently see. And so the search continues. Let me take you to one more place before we move on. Let me show you another way physicists are looking for new physics, another approach that does not involve building larger colliders or sending detectors deep underground. This approach involves atoms, ordinary atoms, atoms that have been cooled to near absolute zero and trapped in electromagnetic fields and probed with lasers of extraordinary precision. In laboratories around the world, physicists are measuring the properties of atoms to levels of accuracy that would have seemed impossible a generation ago. They are looking for tiny deviations from the predictions of quantum mechanics and the Standard Model. They are searching for shifts in energy levels, forbidden transitions, violations of symmetries. They are using atoms as detectors for new physics. One of the most sensitive searches involves the electron's electric dipole moment. This is a quantity that measures whether the electron's charge distribution is perfectly spherical or slightly asymmetric, whether the electron is, in a sense, slightly egg-shaped rather than perfectly round. The Standard Model predicts that the electron should have an incredibly tiny electric dipole moment, so small that it is essentially unmeasurable with current technology. But theories beyond the Standard Model, theories with new particles and new sources of CP violation, often predict a larger electric dipole moment, a measurable one. So experimentalists have gone looking. They have built exquisitely sensitive apparatus to measure the electron's shape. The best current experiments use molecules rather than atoms, because certain molecular configurations amplify the effect of any dipole moment. A molecule called thorium monoxide, for example, has been used to set the current limit. The electron's electric dipole moment, if it exists, is smaller than about 1 part in 10 to the 29. That is a staggeringly small number. It means the electron is round to an almost unimaginable degree. If you scaled the electron up to the size of the Earth, any asymmetry would be smaller than the width of a single atom. Yet the search continues, because if a larger electric dipole moment were found, if the electron turned out to be even slightly egg-shaped, it would indicate new sources of CP violation, new physics, and that new physics might explain why we exist. Every improvement in the measurement narrows the range of possible theories. Every null result tells us something about what the universe is not. The absence of a signal is itself a clue. This is the nature of frontier physics. It is not just about seeing new things. It is about ruling out possibilities, constraining the unknown, tightening the boundaries around what remains. The electron's roundness is a constraint. The muon's magnetic moment is a hint. The neutrino's mass is a puzzle. Each measurement contributes to a larger picture, a picture that is slowly, painstakingly coming into focus. And through all of this, the question of baryogenesis remains. The standard model cannot explain why we exist. The new physics that could explain it has not yet been found. But the tools to find it are becoming sharper. The experiments are becoming more sensitive. The theories are becoming more constrained. The answer is out there, encoded in particles and forces and symmetries we are only beginning to understand. Now let me pull back once more. Let me try to give you a sense of where all these threads converge. We have talked about the Sakharov conditions, the requirements for creating more matter than antimatter. We have explored leptogenesis and the role of heavy particles in the early universe. We have followed the search for Majorana neutrinos deep underground. We have examined the muon anomaly and the hints of lepton universality violation. We have visited laboratories where atoms are measured to impossible precision. Each of these investigations is distinct. Each has its own methods, its own instruments, its own community of researchers. But they are all asking in different ways the same fundamental question. Why is there something rather than nothing? That question has troubled philosophers for millennia. It has seemed, at times, unanswerable. A question that lies beyond the reach of empirical investigation. A question for theology or metaphysics rather than science. But physics has given it a sharp edge. Physics has shown us that the question has a specific, measurable form. The existence of matter is not guaranteed by any known law. The standard model, our best description of nature, predicts a universe of radiation and nothing else. The fact that atoms exist, that stars exist, that we exist, is a violation of our best theory. It is a crack in the foundation of physics, and cracks are where the light gets in. The matter-antimatter asymmetry is not just a puzzle to be solved, it is a guide. It tells us where to look for physics beyond the standard model. It tells us that CP violation must be larger than we have measured. It tells us that new particles or forces must exist. It tells us that the laws of nature are richer than we currently understand. Every atom in your body is a message from the first moment of time, a message that we are still learning to read. And the reading is proceeding, slowly, carefully, across laboratories and observatories and computing centres around the world. Thousands of physicists are contributing to this effort. Most of them will never see the final answer. That is the nature of deep science. It moves on generational timescales. It requires patience that exceeds individual careers. But it moves. And someday, perhaps in our lifetimes, perhaps not, the answer will come. We will understand what happened in that first fraction of a second. We will know why the universe chose existence. Until then, we watch, we measure, we wonder, and we let the strangeness of our own existence settle into us like a fact that refuses to be ordinary. There is one more direction to explore, one more approach that physicists are taking. It involves looking not at particles in laboratories, but at the sky itself. It involves using the universe as the detector, scanning the cosmos for signals that might reveal the physics of the first instant. Because the matter-antimatter asymmetry did not happen in isolation. It happened at the same time as other processes, the expansion of space, the cooling of the primordial plasma, the formation of the first nuclei. And those processes left marks. They left echoes that we can still detect today. The most famous of those echoes is the cosmic microwave background, the faint glow of radiation left over from when the universe was 380,000 years old. That radiation has been measured with exquisite precision by satellites like Planck and WMAP. Its temperature fluctuations, its polarization patterns, its statistical properties, all have been mapped and analysed. And hidden in that data might be signatures of the physics that created the matter-antimatter asymmetry. Some theories of baryogenesis predict that the process would have produced gravitational waves, ripples in the fabric of space-time itself, generated by violent phase transitions in the early universe. Those gravitational waves would be too faint to detect directly with current instruments, but they would leave an imprint on the cosmic microwave background. A particular pattern of polarization called B-modes. Experiments are searching for this signal. They are looking at the microwave sky from the South Pole, from high-altitude balloons, from ground-based observatories in the Atacama Desert. So far, the primordial B-mode signal has not been found, but the search continues. Other theories predict that the asymmetry would leave slight chemical signatures in the early universe, variations in the abundance of different elements formed in the first minutes after the Big Bang. Physicists are measuring the primordial abundances of hydrogen, helium, deuterium, and lithium, comparing them to the predictions of Big Bang nucleosynthesis. Any deviation might hint at new physics operating at that time. The measurements are difficult. The primordial gas has been processed through generations of stars. Disentangling the original abundances from later contamination requires careful analysis, but the work proceeds, and still other approaches involve looking for antimatter directly. Despite everything we have said about the asymmetry, some physicists have not given up on the possibility that pockets of antimatter might exist somewhere in the universe, perhaps entire anti-galaxies separated from ordinary matter by vast distances. Satellites like AMS-02, mounted on the International Space Station, are searching for anti-helium nuclei in the cosmic rays that strike Earth. Anti-hydrogen would be too fragile to survive the journey through the galaxy, but anti-helium, if it exists, might make it. So far, no anti-helium has been found, but the absence of a signal is itself informative. It tells us that if antimatter regions exist, they are rare and distant. The universe holds its answers gently. The universe holds its answers gently, and we are learning to listen gently in return. There is something almost meditative about this phase of the search. After the violence of collider experiments, after the frantic accumulation of data and the fevered construction of theories, the cosmological approach asks us to simply look, to receive what the universe sends us, to let the ancient light tell its own story, if only we can learn to read its language. The cosmic microwave background is the oldest light we can see, older than the oldest stars, older than the first galaxies. It comes to us from a time when the universe was still a fog of hot plasma, when no structures had yet formed, when the matter-antimatter asymmetry had already done its work and the surviving matter was waiting, just waiting, for the expansion to cool things enough for atoms to form. When that moment finally came, 380,000 years after the beginning, the fog cleared, light was released, and that light has been travelling ever since, cooling and stretching as the universe expanded, until today it arrives at our instruments as a faint microwave whisper, just a few degrees above absolute zero. That whisper carries information. Encoded in its temperature variations are the density fluctuations of the early universe, the seeds that would eventually grow into galaxies and clusters, and the vast cosmic web of structure we see today. Encoded in its polarization are the conditions of the plasma at that ancient time, the way electrons scattered light as they danced in the primordial heat, and possibly, just possibly, encoded in particular patterns of that polarization are the signatures of events that happened much earlier, events from the first trillionth of a second, events that include whatever process created the matter-antimatter asymmetry. The signal physicists are searching for is called a primordial B-mode. It is a particular curl pattern in the polarization of the microwave light, a swirl rather than a radial pattern, and it would be evidence of gravitational waves from the very early universe, ripples in space-time generated by some violent process in the first instance of cosmic history. What kind of process? Several possibilities connect directly to baryogenesis. One involves cosmic phase transitions, moments when the universe cooled through a critical threshold and the fundamental fields reorganized themselves like water freezing into ice. Some theories of baryogenesis predict that these transitions were violent, turbulent, creating bubbles of the new phase that expanded and collided with tremendous energy. Those collisions would have generated gravitational waves, strong ones, and those waves might have left their fingerprint on the microwave background. Another possibility involves cosmic strings, hypothetical one-dimensional defects in the fabric of space-time, thinner than a proton but potentially stretching across the entire observable universe. Some theories predict that cosmic strings formed during the phase transitions of the early universe, and that their oscillations would generate gravitational waves that might also be detectable. The same physics that could explain baryogenesis could leave multiple signatures, if we know where to look. The search for primordial B-modes has been going on for over a decade now. In 2014, a team using the BICEP 2 telescope at the South Pole announced a detection. For a few weeks, the physics community was electrified. If the signal was real, it would have been one of the most important discoveries in the history of cosmology. But follow-up analysis revealed that the signal was likely due to dust in our own galaxy, tiny grains of material between the stars emitting their own polarized light that mimicked the primordial pattern. The announcement was retracted. The search continued. Today, more sensitive experiments are underway. BICEP 3 and the Keck Array at the South Pole, the Simons Observatory in Chile, the planned Lightbird satellite. Each generation of instruments pushes the sensitivity lower, looking for fainter and fainter signals, trying to separate the genuine primordial signature from the foreground contamination of our own galaxy. It is painstaking work, it requires extraordinary care, and it may take years or decades more before a definitive answer emerges. But this is how we learn what happened at the beginning. Not through direct observation. The light from that era was absorbed by the primordial plasma, invisible to us forever, but through its effects, through the echoes it left in later phenomena. The early universe wrote its story into everything that followed, and we are slowly, patiently learning to read the text. There is another echo that connects us to the first moments. It involves not light, but matter itself. The abundances of the lightest elements, hydrogen, helium, deuterium, lithium, were fixed in the first few minutes after the Big Bang, in a process called Big Bang nucleosynthesis. The universe was hot enough for nuclear fusion, but cool enough for newly formed nuclei to survive. For about 20 minutes, fusion proceeded, converting protons and neutrons into helium, and trace amounts of heavier elements. Then the universe cooled further, fusion stopped, and the primordial composition was locked in. That composition depends on the physics of that era. It depends on how many protons and neutrons existed. It depends on the expansion rate of the universe, which controlled how long the fusion window stayed open, and crucially, it depends on the number of types of neutrinos, lightweight particles that were abundant in the early plasma and affected the balance between protons and neutrons. Physicists have measured the primordial abundances by looking at the oldest, most pristine gas clouds in the universe, regions that have never been inside a star, never been processed by stellar fusion, retaining their original composition from those first minutes. The measurements agree remarkably well with the predictions of Big Bang nuclear synthesis, assuming 3 types of neutrinos and the matter density we infer from other observations. It is one of the great successes of modern cosmology. But the agreement is not perfect. There is a puzzle involving lithium. The predicted abundance of lithium-7, based on standard physics, is about 3 times higher than what we observe in old stars. This is called the cosmological lithium problem, and it has persisted for decades. Most physicists believe it reflects some astrophysical process, stars destroying lithium in their outer layers perhaps, or our measurements of old stars being biased in some way. But some have wondered whether it might be a hint of new physics. Physics that operated in the first minutes. Physics that might be connected to the same processes that created the matter-antimatter asymmetry. The connection is speculative, but it reminds us that the early universe was not a collection of isolated events. Everything happened together, intertwined, each process affecting the others. The baryon asymmetry was established. Then the universe cooled, and the quarks bound into protons and neutrons. Then the universe cooled further, and the protons and neutrons fused into light nuclei. Then the universe cooled further still, and the nuclei captured electrons to form atoms. Then the light was released. Each stage depended on what came before. Each stage left its mark on what followed. If we could unravel all those marks completely, we could reconstruct the physics of the first instant with extraordinary precision. We are not there yet. We may never be there completely. But each new measurement, each new observation, brings us closer to the truth. And then there are the direct searches for antimatter in the cosmos. We have said that the asymmetry was total, that the matter won completely, leaving no macroscopic antimatter anywhere in the observable universe. But how do we know that for certain? How do we know there are no anti-galaxies, no anti-clusters, hidden somewhere in the cosmic distance? The argument is straightforward. If regions of matter and antimatter coexisted in the early universe, they would have eventually come into contact. And where they met, annihilation would occur. Not the gentle, one particle at a time annihilation of a laboratory, but vast conflagrations at the boundaries between domains. Those annihilations would produce gamma rays, high-energy light that we could detect from across the universe, and we would see them as bright lines at the boundaries between matter and antimatter regions, cosmic firewalls visible to our gamma-ray telescopes. We do not see them. The gamma-ray sky shows no such boundaries. The conclusion is that if antimatter regions exist, they must be incredibly rare and incredibly distant, so far apart that they have not yet had time to come into contact with ordinary matter. Given the age of the universe and the distances involved, this would require the antimatter regions to be outside our observable horizon. Effectively, they would not exist for us at all. But the search continues anyway, because science does not rely on arguments alone. It relies on observations, and the most direct way to know whether antimatter exists in the cosmos is to go looking for it. The AMS-02 experiment, the Alpha Magnetic Spectrometer, has been mounted on the International Space Station since 2011. It is a particle physics detector in space, designed to capture and analyse the cosmic rays that constantly stream through our solar system. Cosmic rays are mostly protons, the nuclei of hydrogen atoms, but they also include heavier nuclei, electrons and positrons, and very occasionally they include antiparticles. The AMS has detected positrons and antiprotons in the cosmic ray flux which is expected. These particles are produced when ordinary cosmic rays collide with gas in the interstellar medium. The collisions create matter-antimatter pairs, and the antimatter particles join the cosmic ray population. Finding them tells us about the collisions, not about primordial antimatter. But antihelium would be different. A single antihelium nucleus, 2 antiprotons and 1 or 2 antineutrons, would be extraordinarily difficult to produce in random cosmic ray collisions. The probability is vanishingly small. Finding antihelium in the cosmic rays would be strong evidence for primordial antimatter, either produced in the Big Bang or in the cores of antistars somewhere in the galaxy. The AMS team has reported hints, a handful of events that might be antihelium, detected over years of observation. But the analysis is complex. The detector was not designed specifically for antihelium, and there are possible backgrounds and instrumental effects that must be carefully ruled out. As of now, no confirmed detection has been announced. The hints remain hints. The search continues. If antihelium were ever definitively detected, it would transform our understanding. It would mean that the matter-antimatter asymmetry was not complete, not universal. It would mean that pockets of antimatter survived somewhere, somehow, despite all our theoretical expectations. It would open a new chapter in the story of the universe's origin, or the search might return only silence. Year after year, decade after decade, no antihelium, no anti-galaxies, no antimatter domains anywhere in the observable cosmos. That silence would be its own kind of answer. It would tell us that the asymmetry was indeed total, that whatever process created it was thorough and final, that the universe really did choose matter, once and for all in that first fleeting instant. Either answer would be profound. The search is worth conducting regardless of the outcome, and so we find ourselves at the edge of what can currently be known. The laboratories push forward, building more sensitive detectors, more powerful accelerators, more precise measurements. The theorists push forward, constructing new models, exploring new mechanisms, trying to connect the abstract mathematics of particle physics to the concrete fact of our existence. The astronomers push forward, scanning the skies for signals from the ancient past, reading the echoes left by events that occurred before stars or galaxies or even atoms existed. Somewhere in this vast collective effort lies the answer. The reason we exist. The mechanism that created the asymmetry. The physics that chose existence over annihilation. We do not have that answer yet. We may not have it for a long time. The standard model is almost certainly incomplete, but we do not yet know how to complete it. Every extension, every new theory, every proposed mechanism carries risks. The risk of being wrong, the risk of making predictions that cannot be tested, the risk of leading physics into a dead end. The path forward is uncertain, but uncertainty is not ignorance. We know vastly more than we did a century ago, when physicists first began to understand the structure of the atom. We know more than we did 50 years ago, when the cosmic microwave background was first detected and the Big Bang theory was confirmed. We know more than we did 20 years ago, when the experiments proving CP violation earned their Nobel Prize. Each generation adds to the understanding. Each discovery constrains the possibilities. The space of viable theories shrinks. Even as the difficulty of the remaining questions grows, this is the patient work of science, not the dramatic breakthroughs of popular imagination, not the sudden revelations, but the slow accumulation of evidence, the gradual refinement of understanding, the steady march toward truth. It moves on timescales that exceed individual careers, sometimes individual generations, but it moves. And there is something beautiful about participating in that movement, even from the outside, even as observers who will never run an experiment or derive an equation. We are witnesses to one of the deepest questions humanity has ever asked. Why is there something rather than nothing? Why does the universe contain matter at all? Why are we here to ask? The fact that we can ask those questions, that we have developed the tools and concepts to even frame them properly, is itself remarkable. For most of human history, these questions were the province of philosophy and theology. The idea that physics could address them directly, that we could build machines and conduct experiments to probe the origin of matter itself, would have seemed fantastical. Yet here we are. We have colliders that recreate the conditions of the first microsecond. We have detectors sensitive to single antiprotons. We have telescopes that capture light from when the universe was a baby. We have turned the deepest existential questions into research programs. That is the wonder of this particular moment in history. Not that we have the answers, but that we have the questions in precise form. Not that we understand everything, but that we understand what we do not understand. The mystery has been measured. The unknown has been mapped. And the map shows where the treasures might be buried, even if we have not yet dug them up. Let that settle for a moment. We are a species that emerged from cosmic accident, from the tiny leftover fraction that did not annihilate from the one particle in a billion that survived. And we have used the matter we are made of to build instruments that probe the origin of matter itself. We have turned our existence into a question, and we are using our existence to answer it. There is something circular about that, something almost paradoxical. The universe, through us, is investigating how the universe came to produce us. The night sky offers no easy comfort here. The stars burn silently, giving no hint of the violence that birthed them. The cosmic microwave background whispers its ancient message, but the whisper is faint, encoded in patterns we can barely detect. The laboratories hum with their billion-dollar machines, smashing particles together trillions of times, searching for the rare events that might reveal new physics. And somewhere out there, in the space between galaxies or in the physics we have not yet discovered, lies the answer. We are patient because we must be. We are persistent because the question matters. And we continue, generation after generation, adding our small contributions to the great collective effort, trusting that someday the pieces will fit together and the picture will become clear. The universe chose existence. We do not yet know why, but we know that the choice was made, and we are the evidence that it was made well enough for wandering beings to emerge, to look back at the beginning, and to ask what happened there. That is no small thing. That is, in its own quiet way, extraordinary. The search continues, the measurements proceed, the patience holds, and the strangeness of our existence, the sheer improbability of matter surviving at all, settles into us not as a problem to be solved, but as a condition to be inhabited. We are here, against all odds, against all the annihilation that should have occurred. We are here, and we are looking for the reason. Perhaps the most fitting place to end this journey is not in a laboratory at all, not beneath the mountains of Japan or in the tunnels under Geneva, not in the control rooms where physicists watch their screens, waiting for the rare event that might change everything. Perhaps the most fitting place to end is somewhere much simpler, much older, much closer to the condition we have been describing all along. Picture a clearing on a summer night, the kind of place where the sky opens up and the stars reveal themselves in their full multitude. You have been there, or somewhere like it, away from the cities, away from the lights, in one of those rare dark places where the Milky Way still stretches overhead like a river of luminous dust. Lie back, let your eyes adjust, give them 10 minutes, 15, until the faintest stars begin to emerge from the background darkness, until the sky deepens and fills with light that has been travelling for years, centuries, millennia to reach you. Every point of light you see is matter. Hydrogen burning into helium, helium fusing into carbon, carbon collapsing into oxygen, into silicon, into iron. Every star is a furnace converting the primordial elements into the heavier ones that will someday form planets, form rocks, form the bones of creatures not yet born. Every photon that enters your eye carries information about nuclear reactions happening millions of years ago, information encoded in wavelengths and intensities, information that your neurons process without any conscious effort, transforming electromagnetic radiation into the experience of beauty. You are made of the same material as those stars, not metaphorically, literally. The iron in your blood was forged in the core of a massive star that exploded before the sun was born. The calcium in your bones came from stellar furnaces that burned out billions of years ago. The oxygen you are breathing right now was manufactured in the nuclear reactions of a generation of stars that no longer exists. All of that matter, the matter in the stars, the matter in your body, the matter in the ground beneath you and the air around you, all of it traces back to the same moment, the same asymmetry, the same unexplained excess that allowed anything to survive at all. When you look at the night sky, you are looking at the evidence of baryogenesis. Every star is a reminder that the universe chose existence. Every galaxy is a testimony to the leftover fraction, the one part in a billion that did not annihilate. The darkness between the stars is where the annihilation would have been complete, where matter and antimatter would have met and vanished, leaving nothing but radiation and emptiness forever. But something happened. Something intervened. Something tilted the scales just enough for matter to win, for structure to form, for stars to ignite, for planets to coalesce, for life to emerge, for you to lie here in this clearing looking up at the evidence of your own improbability. Rest with that for a moment. The night sky is not just beautiful, it is a message, a record of the greatest mystery in physics, written in the language of light and matter and time. Every star is asking the question we have been asking throughout this journey. Why am I here? Why did I survive? What happened at the beginning that made existence possible? The stars cannot answer. The sky cannot explain. The universe keeps its secrets well. But the fact that the questions can be asked, the fact that there are minds here capable of framing them, of building instruments to probe them, of dedicating entire careers to their pursuit, that fact is itself part of the answer, or at least part of the mystery. Because here is the strangest thing of all, the thing we have been circling around without quite naming it directly. The universe did not have to produce questioning beings. The matter that survived could have remained simple forever. Hydrogen could have drifted in clouds for eternity without ever condensing into stars. Stars could have burned without ever producing planets. Planets could have remained barren rocks, geologically active perhaps, but chemically inert. Life could have stayed microscopic, could have remained single-celled, could have achieved complexity without ever achieving consciousness, but it did not. Somehow the matter that survived the great annihilation arranged itself into beings that wonder about the annihilation. Somehow the leftover fraction produced creatures capable of measuring the ratio that allowed them to exist. Somehow the universe developed the capacity to investigate itself. This is not a logical necessity. There is no law of physics that requires consciousness to emerge from matter. There is no equation that predicts minds will arise from molecules. The fact that it happened here, on this small planet, in this unremarkable corner of an unremarkable galaxy, that fact adds another layer of mystery on top of the original one. We do not just need to explain why matter survived. We need to explain why matter eventually wondered about its own survival. Some physicists and philosophers have tried to connect these two mysteries, have argued that a universe without observers is somehow incomplete, that consciousness plays a role in the fabric of reality itself. This is the territory of the anthropic principle, of quantum measurement puzzles, of ideas that hover at the boundary between physics and philosophy. We do not have the time or space to explore them fully here, but it is worth noting that the mystery of baryogenesis intersects with these deeper questions about the relationship between mind and cosmos. Why is there something rather than nothing? And why is some of that something capable of asking why? Let those questions hold you gently. They are not demands, they are invitations. They are windows into the strangeness of existence, the improbability of matter, the miracle of minds. You do not need to answer them. No one needs to answer them tonight. They are questions to carry, to live with, to return to in quiet moments, when the world seems ordinary and you need a reminder that it is not. The physicists will continue their work, The experiments will continue to run. Dune will gather its data over the coming decades. The next generation of colliders will probe energies we can barely imagine today. Theorists will propose new mechanisms, new particles, new symmetry violations. Some ideas will be confirmed, most will be ruled out. The search will narrow, or perhaps it will widen, revealing new complexities we had not anticipated. And somewhere in that ongoing effort the answer may emerge. 100 years from now, perhaps 200, perhaps tomorrow, though probably not tomorrow, someone may piece together the final clues. Someone may understand why the universe tilted toward matter rather than antimatter, why existence was chosen over annihilation, why anything is here at all. What will that moment feel like? What will it mean to finally know? Perhaps it will feel like coming home, like recognizing something that was always there, hidden just beneath the surface waiting to be discovered. The great mysteries of science often feel that way in retrospect, as though the answer was obvious once you knew where to look. Relativity seems inevitable now. Quantum mechanics seems natural to those who grew up with it. The structure of DNA seems almost simple in its elegance. Perhaps baryogenesis will feel the same way, once we understand it. Perhaps we will look back at our confusion and marvel that it took so long to see what was right in front of us. Or perhaps it will feel like vertigo, like standing at the edge of something incomprehensibly vast. The answer to baryogenesis may reveal that our universe is one among countless others, that the laws of physics are not fixed but variable, that existence itself is stranger than any science fiction ever imagined. The truth may not comfort us. It may not fit neatly into our existing frameworks. It may require us to revise not just our physics but our philosophy, our understanding of what it means to be real. We cannot know in advance which way it will go. We cannot know whether the answer will be elegant or bizarre, simple or complex, satisfying or deeply unsettling. That uncertainty is part of the adventure. That not knowing is part of being alive at this moment in the story. Because we are at a particular moment, an unrepeatable one. We are the generations who know the question but not the answer. We are the ones who have measured the asymmetry without understanding it. We are suspended between ignorance and knowledge, between ancient darkness and future light. Future generations may look back at us with the same mixture of affection and pity that we reserve for medieval scholars who thought the earth was at the centre of everything. They may marvel at how much we did not know, how much we got wrong, how close we were without seeing. But they will not have what we have. They will not have the privilege of wonder. Once the answer is known, it cannot be unknown. Once the mystery is solved, it cannot be unsolved. The generations that follow us will inherit certainty. We inhabit possibility. There is something precious about that, something worth savouring. We are living in the time when baryogenesis is still an open question, when the origin of matter is still a frontier, when every new experiment might reveal something transformative. We are witnesses to the search, not just inheritors of the result. Let your breathing slow. Let the night settle around you. Let the stars continue their silent burning overhead, indifferent to the questions they provoke, indifferent to the minds that study them. They will burn for billions of years more. They do not need to know why they exist. They simply exist, and their existence is enough. But you are different. You carry the question with you. You wonder. You ask. You look at the universe and demand an explanation, even knowing that the universe owes you nothing, that the cosmos operates without concern for your curiosity, that the laws of physics do not adjust themselves to satisfy human understanding. You ask anyway. And that asking is itself a form of participation, a form of engagement with the deepest structures of reality. When you wonder why there is something rather than nothing, you are doing what the universe cannot do for itself. You are reflecting on existence. You are making consciousness a fact of the cosmos, a feature of reality, a presence that was not there at the beginning but is here now. The universe is approximately 13.8 billion years old. For most of that time, there was no one to ask questions. For billions of years, stars burned and galaxies collided, and matter arranged itself into complex structures, all of it happening in silence, without observation, without wonder. The universe was magnificent and empty, a cathedral with no congregation, a symphony with no audience, and then, somewhere, somehow, matter arranged itself into minds. Eyes opened, neurons fired, thoughts emerged, and for the first time in all those billions of years the universe was known, For the first time, existence was recognized, reflected upon, questioned. That happened here, on this small planet, in this unremarkable corner of an unremarkable galaxy. We do not know if it happened anywhere else. The silence of the cosmos suggests, but does not prove, that we might be rare, perhaps even unique. Perhaps we are the only place where matter wonders about itself. If that is true, and we do not know if it is true, then we are precious beyond measure. We are the universe's way of understanding itself. We are the matter that survived, arranged into the only form that can ask why it survived. And if we are not alone, if somewhere out there other minds emerged from other collections of leftover matter, other consciousnesses arose on other worlds around other stars, then we are part of something larger, a community of questioners spread across the galaxy or the universe, all of us grappling with the same mysteries, all of us heirs to the same asymmetry, all of us made of matter that should not exist. Either way, we matter. The pun is intentional. The search for baryogenesis is the search for our origin, not just our human origin or our planetary origin, but the origin of matter itself, the origin of everything that is rather than everything that could have been, which is nothing. When physicists probe CP violation or design detectors for leptogenesis, they are doing more than satisfying curiosity. They are investigating the foundation. They are asking why there is a universe capable of containing physics and physicists, experiments and experimenters, questions and questioners. The answer, when it comes, will not tell us how to live. It will not resolve our moral dilemmas or heal our political divisions or make our personal struggles easier. It will not explain why we suffer or how we should love or what happens when we die. Those questions belong to other domains, other kinds of inquiry. Physics cannot answer them, and it should not pretend to. But the answer will tell us something. It will tell us that we belong here, that our existence is not a mistake, not an accident in the careless sense, but the result of something, some process, some mechanism, some law, that made matter possible. It will tell us that the universe, in some sense, was ready for us, that the conditions were right, that existence was not arbitrary, but was, in some deep sense, chosen, not chosen by a mind, not chosen by a god, chosen by physics, by the way the laws work, by the symmetries that break, by the particles that exist and the interactions they undergo. The universe chose matter over antimatter through whatever process baryogenesis turns out to be, and that choice made everything else possible. The stars, the planets, the oceans, the continents, the forests and the deserts and the creatures that inhabit them, the cities and the libraries and the laboratories. You, lying in this clearing, looking up at the light of ancient suns, all of it traces back to that moment, that asymmetry, that leftover fraction. The night is deep now. The stars have fully emerged. The Milky Way arches overhead, 200 billion suns suspended in a spiral arm of a galaxy that is itself one among hundreds of billions. The scale is almost too large to comprehend. The numbers resist imagination, but you do not need to comprehend it. You do not need to understand every detail or follow every calculation. You need only know that you are part of it, that your matter is the same matter that fills the stars, that your existence is the same existence that fills the cosmos, that the question you carry, why is there something rather than nothing, is the same question the universe embodies every moment it continues to exist. Let your eyes close if they want to. Let the darkness settle in. Let the night take you wherever it wants to take you, into sleep or dreams or simply deeper rest. The matter that composes you will continue regardless. Your atoms do not sleep. Your electrons do not rest. The quantum fields that constitute your being fluctuate on timescales too short to measure, persist on timescales too long to imagine. You are temporary in one sense, you are eternal in another. The matter that you are was here before you were born, and will be here after you die, rearranged into other forms, participating in other stories, asking other questions. For now, it is you. For now, it wanders through you. For now, the leftover fraction from the first microsecond looks up at the night sky and asks where it came from. The universe does not answer. The stars burn on in their ancient silence. The cosmic microwave background whispers its faint message, too quiet for human ears, too encoded for casual understanding. The laboratories stand ready, their detectors waiting, their scientists sleeping or working through the night, adding their small contributions to the great collective effort. And somewhere in the space between what we know and what we do not know, the answer waits. Patient, untroubled by our confusion, present in the structure of reality itself. If only we knew where to look, we will find it, or our children will, or their children after them. Baryogenesis will yield its secret eventually. The question will become an answer. The mystery will become history. Until then, we carry the wonder with us. We inhabit the uncertainty. We look at the night sky and remember that nothing about this was inevitable. Matter could have annihilated completely. The universe could have ended in the first second. Existence was not guaranteed, but it happened. Against all probability, against all the annihilation that physics predicted, it happened. Matter won. Structure formed. Stars ignited. Planets coalesced. Life emerged. Minds arose. And now, on this small planet, in this quiet clearing, under this ancient light, you lie awake or drifting towards sleep, carrying the question that connects you to the beginning of everything. Why is there something rather than nothing? We do not know, not yet, but the fact that we can ask, the fact that we are here to ask, made of matter that should not exist, wondering about the asymmetry that made us possible, that fact is its own kind of answer. Something happened. We are the proof. And as long as we continue to wonder, the question remains alive, the mystery remains honoured, and the universe continues to know itself through us. The stars burn on, the silence holds, and the strangeness of existence settles over you like a blanket, not as a problem to be solved, but as a gift to be received. You are here. Against all odds, you are here, and that is no small thing.